This is a recording of notes for our beginning of Chapter 8 for hours 5 and 6. You'll be going through this on Thursday, April 11th, because we got out of school early on Wednesday and you did not have this. Second hour did have go through this part of notes. So the teacher should be giving you a handout for homework 0, and in 5th and 6th hour, homework 0 will be due for you on Monday. You'll just push everything back one day compared to our original plan as we go. And so this is the beginning of Chapter 8, but we're going back all the way to the beginning of the book to 09, and it's square roots and simplifying radicals. This is something you've done before, but we're going over it now. The teacher should give you a handout for the homework and also a handout for the key terms page that I'll put up in just a minute. So and then we'll go over that key terms page. So again, this is just for 5th and 6th hour. I am going to go through this a little bit quickly, so please make sure that you're pausing this recording as you need to so that you can get things written down. So this is 09, square roots and simplifying radicals. The essential question, can you evaluate square roots and simplify radical expressions? So if you need to look at that longer, please make sure that you pause this, because I'm going to go to the next slide, which will be the key terms page. Here's the key terms page, and I will go through that a little bit with you. If we were all here together, I would have students read it, but I will just read through it. So a radical expression, and this is on a handout. You should have the handout. You're just adding in the things that I added in with marker and on your handout, and then this can go on your key terms page. A radical expression is an expression that contains a square root. The expression is in simplest form when the following 3 conditions have been met. No radicand, that's the symbol, the square root symbol. No radicand crayons have perfect square factors other than 1. And so you can kind of see this. This was the square root of 25. And so for the square root of 25, that's not in simple radical form because it's equal to 5. And you can see that answer is right here. I'll maybe write in yellow. Likewise, this says the square root of 50 is not allowed, because think about the fact that 50 is 25 times 2, so it has a factor that is a perfect square as we look at that. Then no radicands contain fractions, so we can't have the square root of 1/5, so kind of write that on your notes as well. And then the last one here is no radicals appear in the denominator of a fraction. So the denominator, remember, is the bottom of a fraction. So if I have 3 over the square root of 2, that's not allowed because I have a radical down there. And we'll talk about how to handle these things as we go. The product property states that for 2 numbers a and b, b greater than or equal to 0, a and b are both greater than or equal to 0, the square root of ab is equal to the square root of a times the square root of b. And so sometimes we'll either have them together and we'll separate them to help us put things in simple radical form, or we'll have 2 things and we'll actually multiply them to get an answer as we go. So those are different things that can happen there. Going down on this, for radical expressions in which the exponent of the variable inside the radical sign is even and the resulting simplified exponent is odd, you must use absolute value to ensure non-negative results. So this is I call it the even, odd. When we're doing square roots, that is the square root, and squaring is kind of an even power. And so this is an even radical. The actual radical is even. As you go in further in math, sometimes there will be other roots not that way. And then if the variable, and this is for when we have variable expressions, if the variable is raised to an even power in here, and then when you get the answer, it ends up to have an odd power, then we have to put it in absolute values so that we make sure that we're not getting the square root of a negative, and maybe you remember that from other work that you've done. Square root of a negative, if you try to do that on your calculator, you get undefined, which we'll handle that as well when you get to higher math. And the quotient property states that for any numbers a and b, where a is greater than or equal to 0 and b is greater than or equal to 0, the square root of a over b is equal to the square root of a over the square root of b. So we can take a fraction that's under the radical and we can change it so both the top, the numerator, and the bottom, the denominator, have their own radicals as we go. Then rationalizing the denominator of a radical expression is a method to use to eliminate radicals from the denominator of the fraction, and that has to be done in order to have it in simple radical form. To rationalize the denominator, multiply the expression by a fraction equivalent to 1 such that the resulting denominator is a perfect square, and we'll talk about that as we go. Now, sometimes conjugates are used to simplify radical expressions, and conjugates are binomials of the form p the square root of q plus r the square root of t, and p the square root of q minus r the square root of t. Notice the beginning value is identical, and then you're either adding or subtracting that ending value as you go. Then just a reminder about conjugates in general. First of all, if you remember multiplying something by like x plus 3 times x minus 3, and when you multiply that, you distribute that. X times x is x squared. X times negative 3 is minus 3x. And then 3 times x is 3x, so we get plus 3x. And 3 times negative 3 is minus 9. And so that is what we get in that instance. And let me get rid of some of those. And then notice that the 3's plus 3x and minus 3x cancel each other out, and we get x squared minus 9. And so back in algebra, you learned a rule that says if you take a plus b times a minus b, you get a squared minus b squared. And so that is something that you'll be using when you use conjugates. So if you look at these conjugates, you're just writing them in your notes on that key terms page handout right now. 3 plus the square root of 2 and 3 minus the square root of 2 would be conjugates. Notice that first part is identical, and then the second part is an added square root of 2 and a subtracted square root of 2. So that's what conjugates look like, and we'll have a problem like that. Now, for the actual notes for this section, it's not like a geometry section. It's really a review of algebra, and so we don't have a handout for those. We're just going to write these problems as we go. So I'll rewrite the problems as we look at them. So 1a is to simplify the square root of 45. And so the way that we're going to do that is we're going to use a factor tree. And so you should be familiar with that as you go. And so if I take 45, I need two things that multiply to be 45. What comes to mind is 5 times 9. 5 is prime. I just leave it. 9 is 3 times 3. And so when I write that, I'm going to write it as 3 squared times 5. That's how I'm going to rewrite 45. So square root of 45 is equal to the square root of 3 squared times 5. I generally put the perfect square, so this is going to come out of the radical. I generally put that in the front so that So that's what I have. And then I'm going to rewrite that as two radicals, the square root of 3 squared times the square root of 5. And then the square root of 3 squared is equal to 3. And so we get 3 the square root of 5. And that's the answer to that first problem as we go. So we'll just keep going through these. And if you need to pause this, you can. Otherwise, we'll just keep working. 1b is the square root of 6 times the square root of 15. So the first thing I might do is just multiply 6 times 15. I could put them both under the same radical and find their prime factorization, but I'm going to multiply them. And so this is the square root of 90 when you multiply 6 times 15. Then I'm going to do that factor tree again, 90. What comes to mind is 9 times 10, and then 9 is 3 times 3, 10 is 2 times 5. So I'm going to say 90 is equal to 3 squared times 2 times 5. So I'm going to rewrite the square root of 90 as the square root of 3 squared times 2 times 5. We can only take perfect square factors out of radicals, so things that are squared can come out, or even to the 4th power, or some even power. So when I have that 2 and 5, they're going to kind of be staying in that radical, and so I'm going to rewrite it as the square root of 3 squared times the square root of 2 times 5. I'm leaving the 2 times 5 together because they're not going to come out of the radical. I have the square root of 3 squared separate because the square root of 3 squared is plain old 3. And square root of, since the 2 and 5 are both prime, neither can come out, so that will be 3 the square root of 10. And that's how we use that product property and take out perfect square factors, just to kind of let you know as we look at that. Now, the next problem has some variables in it. So this is problem number 2, and our directions are simplify. It's the square root of 20, x to the 3rd, y to the 5th, z to the 6th. Now, I do have a Janet Jones method that I use here, and when I separate these into their prime factorization and into perfect squares, I take this and I put all the perfect squares in the front because those are going to come out, and then times, and then I put the rest of the factors in the back because they're not going to come out. The book authors always just put all the numbers first, then all the x's, then the y's, then the z's. And then I rewrite it as the square root of the perfect squares, times the square root of the rest of the factors. And then these will stay in the radical, this rest of the factors. And the things that will come out here will be just numbers and variables because they get to come out of the radical. So that's kind of just to let you know how I'm going to do this. And then I'm going to do that factor tree again for 20. I'll just put that over here. 20 is 4 times 5, and so 4 is 2 times 2, and then times 5. So just a little reminder of factor trees, things like that. So 20 is equal to 2 to the 2nd times 5. So when I come over here to my radical on this left side, I'm going to write a really long radical, and I'm going to write these all as perfect square factors and then not perfect square, the rest of the factors. So 20 is 2 squared times 5. So I'm going to separate them. I'm going to put 2 squared toward the front, and I'm going to go like kind of to the middle back, and I'm just going to put the 5 way back there as we go. And then I'm just going to remind you, so I'll kind of talk through some of these. I'll use this little bottom area as some scratch paper. So just a reminder, x to the 3rd is x times x times x. And so x squared is a perfect square times x. So x 3rd x to the third is x squared times x. So I'm going to put the x squared in the front because that's a perfect square, and I'm going to put the other x in the back. And then I'll do the same thing with y to the fifth. So remember, y to the fifth is y times y times y times y times y. And so there's 5 of them multiplied. And so this is y squared times y squared, and then times y. And so these are the perfect square factors, and that's not. So I'm going to go y squared times y squared, and then that last y I'll put way in the back there. And then I'm going to do the same thing with z to the sixth. Z to the sixth, just a reminder, is z times z times z times z times z times z. And so this is z squared times z squared times z squared. And so those are all perfect square factors. I'm going to write them to the front. So z squared times z squared times z squared. We'll talk about methods to shorten this up as we go through, and once we get the answer, we'll give ourselves some options. Now I'm going to take all of these perfect square factors and write them as individual square roots, and then this one, that square root of 5xy, that's going to stay just kind of in the back there. So let me kind of take a minute and do that. So this is going to be the square root of 2 squared times the square root of x squared times the square root of y squared times the square root of y squared times the square root of z squared times the square root of z squared times the square root of z squared times the square root of 5xy. All those are the rest of the factors that are not going to be perfect square factors. Now I'm going to take out of the radical all the perfect square factors. So the square root of 2 squared is just 2 times x times y times y times z times z times z, the square root of 5xy. Now I'm going to kind of rewrite these factors a little better. So that's 2xy squared, z to the third, the square root of 5xy. Now, one thing, because I have variables, I want to look at my even, odd kind of idea that I've had here. Oops. And let me just clone that a second. And I'm going to slide it way down here so that I can see the original problem. So when I look at this original problem, I'm just going to notice some things about it. And I'm going to notice that this is an even square root, so that's an even power. And I'm looking for that even, odd rule. Even, odd rule. And so this is an even power. This is not an even power, so I don't have to worry about that. That's not an even power. I don't have to worry about that. This is an even power. And then when I look at what I got for z as my answer, notice I get an odd power as my answer right there. And so that means I have to put the absolute value bars over that as we go. And so I'm just going to rewrite the problem and the answer. So this one was the square root of 20, x to the third, y to the fifth, z to the sixth, and it's equal to 2x y squared, the absolute value of z to the third, the square root of 5xy. That's the answer that we get for this problem. And now take a minute and look at that and see if you can come up with a little easier way to find these powers that come out. Notice x to the third right here, and I'll write in yellow and then get rid of that. X to the third was x squared times x, so this comes out as just a plain x. That one stayed way in there. Think of at y to the fifth now as maybe even y to the fourth times y. This is the y that stays in by itself. And then if we take y to the fourth and divide by 2, we get y squared. So you could kind of do it that way. But by all means, if you look at the top of the slide right now, that if you write it all out like that, that will work absolutely wonderfully. And just if you notice, let me get rid of some of that yellow first. Just if you notice z to the sixth, when it comes out, it's z to the third, and since it's odd, it's in the radical sign as well. So just some things to remember, and you've done problems like this last year, but it's been a while, and so we want to kind of review that, because in chapter 8 we will want to get things in simple radical form. Then example 3 is to simplify the square root of 25 over 16. And if I was here when I went over this with you, I would say to you, do you recognize 25 as a perfect square and 16 as a perfect square? And I do. I know the square root of 25 is 5, and I know the square root of 16 is 4. So when I look at that, I know it's 5 over 4 outside of the radical. But if I'm not sure, I can rewrite it. 25 is 5 squared. 16, if I do my little factor tree, is 4 times 4, but then that's 2 times 2 and 2 times 2. So 16 is equal to 2 to the fourth, which I can think of as 2 squared times 2 squared. So this is 2 squared times 2 squared. And then I get the square root of 5 squared over the square root of 2 squared times 2 squared. Notice I took the big radical over that whole thing, and I changed it into a radical on the top and the bottom. If you look at your key terms page, you'll see that that is something that we can do. And then when I simplify that further, the square root of 5 squared is just 5, and the square root of 2 squared times the square root of 2 squared on the bottom. So 5 over the square root of 2 squared is 2. This square root of 2 squared is also 2, so I get 5 over 4. So certainly, if you can just go right to 5 over 4 on that one, by all means do that as you go. So that's the quotient property. We were lucky that those were both perfect squares, so we just could get the answer for that one. Now, the next one is some fractions, and there's radicals in the denominator, which we're not allowed to have. So this is 4a, 2 over the square root of 3. And now, if you remember when I read through that key terms part with you, we said that we can have multiply by something that's equal to 1. And it's like, well, why would I multiply by 1? But in this case, what we want to do is we want to get rid of this radical that's in the denominator. And if I multiply it by the square root of 3, that'll be the square root of 3 squared, which is plain old 3. So that's desirable. But so that I don't change the value of the fraction, if I multiply by the square root of 3 over the square root of 3, that fraction is equal to 1. And so I'm just going to get rid of that, but I'm going to rewrite it. Ooh. And so what I'm going to do is I'm going to take and multiply by the square root of 3 on both the bottom and the top. And I did it in a different color so you can see that that fraction is equal to 1. And just a reminder, you can multiply things inside a radical with things inside a radical, and things outside of a radical with things outside of a radical. And so the 2 has to stay outside, the square root of 3 on the top stays the square root of 3. So when I multiply, I'm multiplying straight across, and I get 2 to the square root of 3 over, and then this is the square root of 3 squared, so that is 2 to the square root of 3 over plane 3. You might want to try to remember that when you multiply the square root of 3 times the square root of 3, you just get an answer of 3. And then you could kind of get that right away without having to do that middle step as well. And just a little reminder of what I had said a few minutes ago. I won't leave this on the board. You can just look at it. If I have 2 the square root of 5 times 5 the square root of 7, I can multiply the things outside with things outside and things inside with things inside. So 2 times 5 is 10. The square root of 5 times the square root of 7 is the square root of 35. And notice 5 is prime, 7 is prime, so 35 is not going to have any perfect square factors. So just keep that in mind. You can multiply and divide things inside the radical with things inside the radical and things outside the radical with things outside the radical. Now, our next problem is 4b, and this one is the square root of 13y over the square root of 18. So a couple things to notice as you look at it. Square root of 13, 13 is a prime number. So that's just done the way that it is. Y is just y. It's going to stay in the, under that radical forever, and so we'll just keep having it under the radical as we go. But the square root of 18, if you look at that one, that can be put in simple radical form. So our first job is to put that in simple radical form, and then we'll rationalize the denominator like we did in 4a. So the first thing I'm going to do is my factor tree. 18, I'm thinking of 9 times 2. 9 is 3 times 3, and then times 2. So 18 is equal to 3 squared times 2. I'll color code this a little bit because I'm going to keep writing in green that things that aren't changing. So that's the square root of 13 over, but then I'll write in blue the square root of 18. Remember, I'm changing that now to 3 squared times 2. And I'm just going to work down. And so for this one, I'll still have the square root of 13y over. And then on the bottom here, I'm going to say that's the square root of 3 squared times the square root of 2. And the square root of 3 squared is plain old 3. So that's going to give me the square root of 13y over. And then on the bottom here now, I'll slide that up a little bit so you can see it a little more easily. That bottom now, the square root of 3 squared is just going to be plain 3. And this is going to stay as the square root of 2. So let me get rid of that. The square root of 3 squared is 3. The square root of 2 just stays the square root of 2. So now I've gotten out all of my perfect square factors. Oh, there's a bell. I've gotten out all of my perfect square factors, but now I notice this. I have that radical in the denominator, and I can't have that. So what I'm going to do is I'm going to now multiply by the square root of 2 on the bottom, but then also on the top so that I don't change the value of anything. And that way I'll be able to rationalize the denominator. So I'll just go to a new color because I've kind of got way too many colors going on here. So when I do this top one, those are all radicals. So I'm just going to multiply the things inside the radical with the things that are inside the radical. So that is going to become the square root of 13y times 2, which is going to be 26y. Over, and then down here I have 3 times the square root of 2 squared, and then the square root of 26y just stays because it's 2 times 13. 2 and 13 are both prime numbers, so there's no perfect square factors. And then on the bottom I have that 3 times the square root of 2 squared is plain old 2. And then I'm going to get the square root of 26y over 6 as we look at that. So now the next thing we're going to do is this last problem, and that is example 5. And this is going to be using the conjugate. So 3 over 5 minus the square root of 2 is our problem. So when we have an added or subtracted thing in our denominator that includes a radical, that's when we have to use the conjugate as we do this. So I'm just going to remind myself that if I have 5 minus the square root of 2, oops, which I didn't write correctly, 5 minus the square root of 2, the conjugate is 5 plus the square root of 2. And so that's what I want to multiply the denominator by. But again, I have to multiply the numerator and the denominator by the same thing so that I'm multiplying by 1. So I'm going to multiply this times 5 plus the square root of 2, and on the top 5 plus the square root of 2. And I am going to say this, 5 plus the square root of 2. I want to make sure that all of my binomials, two-term things, have parentheses around them as we go so that I can use the distributive property and kind of do the things that I know how to do. So when I multiply this, first I'm just going to write it as a big fraction. 3 times 5 plus the square root of 2 over 5 minus the square root of 2 times 5 plus the square root of 2. And so now I'm going to do the distributive property on the bottom, and I'll just kind of think through that, and I'm going to write it over here, 5 minus the square root of 2 times 5 plus the square root of 2. When I have that, I know I'm going to multiply 5 times 5 is 25, and then just kind of think through that next part. This is plus 5 the square root of 2, and then this is minus 5 the square root of 2, so those are going to subtract out, and then minus the square root of 2 squared. So I'm going to get 25 minus the square root of 2 squared is going to be 2. And we had that rule where if we take a plus b times a minus b, we get a squared minus b squared. So I can kind of apply all of that to this problem. And I'm going to erase that because I'm not going to leave it on here because I'm just going to use the fact that I know what is going to happen here as we go. So I'm going to go down a little bit. I'm going to leave the numerator 3 parentheses 5 plus the square root of 2. In case my denominator turns out to be something that might reduce with 3, I want to do that. If not, I'll multiply it out. So if this is the conjugates, I'm going to take 5 times 5, which is 25. I'm going to take the square root of 2 times the square root of 2, which is plain 2. And so on the bottom here, I'm going to have that this is 25 minus 2. And so then I have 3 parentheses. Oops, let me rewrite that. 3 parentheses 5 plus the square root of 2 times 25 minus 2, which is 23. So that won't reduce. So then I'm just going to say, oh, okay, then I'll distribute that 3. 3 times 5 is 15, plus 3 times the square root of 2 is just 3 the square root of 2, all over 23. And that's the answer for that one using the conjugates. So this is the end of the 0.9. If you're in 5th and 6th hour and you have time and this is Thursday maybe, and you have time to start the notes for 8.1, I'd like you to do that now. And then you can get as far as you can to see if you can get that done. In 5th and 6th hour, homework 0 will be due on Monday, and homework 1 won't be due until Tuesday, just for 5th and 6th hour, just to kind of let you know. So that's the end of this recording.